Welcome to the Deep Dive, the show where we take a stack of fascinating sources, unearth their core insights, and distill them into actionable knowledge so you can be instantly well-informed. Have you ever, pondered the seeming magic behind your favorite music streaming service? How it instantly recommends that obscure track you never knew you needed?
Or how an online store seems to anticipate your exact desires,
Hmm.
suggesting products eerily similar to your browsing history just moments before.
Exactly. Even the predictive text on your phone kind of finishing your thoughts before you've even fully typed them. These aren't acts of prescience, right? They are everyday marvels powered by what we call similarity search.
Indeed. Behind these incredibly intuitive and, let's face it, effortless features lies one of the most fundamental and profound challenges in modern computing.
Yeah.
How do you swiftly and accurately find similar things within a truly vast, almost unimaginably large ocean of data?
It's like looking for a specific grain of sand on a beach, but not an identical one, just one that looks really similar.
That's a good way to put it. Imagine searching for a specific type of unique seashell on a beach that stretches for thousands of miles. But the catch is, you're not looking for an identical shell, just one that shares a lot of similar characteristics with the one you have in your hand. It's a problem that, until relatively recently, seemed computationally intractable on the scale required by today's digital world.
And today, we're taking a deep exploration into one of the most powerful, elegant, and frankly revolutionary solutions to this very problem: Hierarchical Navigable Small World, or HNSW.
HNSW. It's an algorithm that acts as a silent architect behind so much of your daily digital life, often seamlessly weaving its magic without you even noticing.
Right. It's the engine powering everything from those personalized recommendations to lightning-fast image searches and even the underlying mechanisms in the newest large language models.
Our mission for this deep exploration is to fully unpack HNSW. We're not just going to tell you what it does, but to delve deeply into how it does it, and perhaps most crucially, understand why it's considered such a transformative breakthrough in managing and navigating massive datasets.
We'll journey from the high-level concepts, using some really intuitive analogies, all the way down to the intricate step-by-step details of its operation, making sure you grasp those fundamental aha moments along the way.
Yeah, we want you to really get the core ideas.
So if you've ever felt overwhelmed by the sheer volume of information out there, or simply wondered about the ingenious engineering that underpins those powerful search engines and recommendation systems, this deep dive is your shortcut to being truly well-informed about a crucial piece of modern technology. Let's start our journey.
Okay, let's unpack this with a core analogy that really brings the essence of HNSW to life. Imagine for a moment you're trying to locate a very specific, perhaps little-known, independent coffee shop nestled somewhere deep within a giant, sprawling metropolis you've never visited before.
Right, a huge city. You wouldn't pull out an old-fashioned paper map and painstakingly check every single street block by block looking for it, would you? I mean, that would be an absolute nightmare, an exercise in futility.
Definitely not. You'd instinctively reach for a smart navigation system, something like Google Maps, right?
Exactly.
And when you open that map, you don't immediately zoom in to see every single alleyway, every individual storefront. Your navigation system intelligently starts you with a zoomed-out, high-level view.
You see the major highways, the arterial roads, the main thoroughfares.
Precisely. This broad perspective quickly guides you into the right general vicinity, the larger district or borough where your coffee shop is likely located. Then, as you get closer to that general area, the system gradually zooms in,
Revealing the smaller streets, the local lanes, until you can pinpoint your exact destination, the specific address of that coffee shop. It's a journey from broad strokes to fine detail.
a multi-layered approach to navigation. That, in a nutshell, is the perfect intuitive analogy for HNSW.
So it's essentially a smart, multi-layered navigation system, but instead of finding physical locations in a city, it efficiently finds similar data points within absolutely massive databases.
It's about being incredibly smart and strategic in its search, rather than exhaustively checking every single possibility.
Which would take forever.
Exactly. So to define it more formally, HNSW is a sophisticated graph-based search algorithm. Now, when we say graph-based, think of it as a complex network. In this network, individual data points are like the nodes. Imagine them as unique addresses or landmarks in our data city.
Okay.
And the edges or links are the connections between these nodes, representing a measure of their similarity or relationship. HNSW constructs a very special kind of network where data points that are semantically or structurally similar are deliberately connected to each other.
And its primary purpose is absolutely critical for modern computing and the scale of data we deal with today. It's engineered to quickly find items that are similar to what you're looking for.
Right. And the quickly part isn't just a preference, it's a necessity. We're talking about delivering results in milliseconds, even when you're sifting through datasets containing billions, even trillions of individual items.
Milliseconds, wow.
Yeah, this speed is what transforms theoretical possibilities into practical, real-time applications.
And where does it really shine?
Where HNSW truly, profoundly excels is when dealing with what computer scientists refer to as high-dimensional data.
Okay, high-dimensional data. That sounds complex. It's not just rows and columns in a spreadsheet, is it?
No, definitely not. Imagine the incredibly complex, abstract characteristics that define the meaning of a sentence. How do you quantify the nuanced essence of a phrase like, the quick brown fox jumps over the lazy dog? You can't just put it into a simple category or give it a single numerical value.
Right, it's got layers of meaning.
Exactly. Instead, what happens is that sophisticated machine learning models, often called embedding models, transform this complex human interpretable data into a dense numerical representation.
Ah, the embedding. We hear that term a lot, so it's like a numerical fingerprint.
That's a great way to think about it. An embedding is a highly compressed, multifaceted numerical fingerprint of the original data. It's a vector, essentially a list of numbers, where each number in that vector is a dimension capturing a subtle nuance or feature of its meaning.
So for a sentence, one dimension might be tone, another topic.
It's grammatical structure, exactly. When we say high-dimensional, we mean these embeddings might have hundreds, even thousands of these individual numbers or dimensions, each contributing to its unique signature in this vast mathematical space.
And this isn't just for text, right? Images, too.
Absolutely. Consider the unique features that make up an image. It's not just a collection of pixels. An image contains information about colors, shapes, textures, the presence and type of objects, lighting conditions, spatial relationships, and so much more.
So many things.
Each of these attributes can be mapped to a dimension within its embedding. So an image of a vintage red car facing left might have hundreds or even thousands of these dimensions defining it in its embedding. And if you're looking for images similar to this specific red car, you're searching across all those hundreds or thousands of dimensions simultaneously.
And music. Same idea.
Same logic applies to the intricate patterns in a piece of music. It's not just individual notes, it's rhythm, tempo, melody, harmony, instrumentation, emotional tone, genre, structure. All these complex characteristics contribute to its dimensions in a data sense.
So when we talk about high-dimensional data, we're really talking about transforming incredibly rich, multifaceted, often abstract concepts into a mathematical format where their closeness or similarity can be rigorously measured.
Exactly. And HNSW is purpose-built to efficiently and effectively search through these incredibly rich, multidimensional data points.
This all sounds incredibly sophisticated, and it is. What's the origin story behind HNSW? Was it a sudden single stroke of genius, or did it build upon decades of prior research? And when did this powerful algorithm first emerge?
That's a great question, and it really highlights the iterative nature of scientific progress. HNSW wasn't an overnight revelation. It was originally described in a truly groundbreaking 2016 research paper titled Efficient and Robust Approximate Nearest Neighbor Search using Hierarchical Navigable Small World Graphs.
Oh, okay, 2016, so relatively recent in the grand scheme.
In terms of widespread adoption, yes. This seminal work was authored by U.A. Malkoff and D.A. Schunen. The paper was initially published on Arch5, which is a common platform for sharing research quickly, and later appeared in the prestigious IE Transactions on Pattern Analysis and Machine Intelligence.
So it quickly gained academic validation. That's important.
Absolutely. The publication of this paper marked a significant, almost watershed moment in the field of similarity search. It offered a solution that was not only incredibly fast, but also remarkably stable and robust, which was a challenge for many prior approximate nearest neighbor algorithms.
Robustness is key.
Definitely. Its impact has been profound. It's been cited over 2,000 times in academic literature in the years since, underscoring its widespread influence and the fundamental computational problem it helped solve so elegantly. It truly moved the needle forward, providing a practical, scalable answer to a long-standing challenge.
So HNSW sounds incredibly advanced, a kind of pinnacle of algorithmic design. But as you said, it didn't just appear out of thin air. It's a testament to clever engineering, taking a foundation of existing powerful concepts and combining them in an ingenious way.
To create something even more amazing, think of it like a master chef taking three incredible high-quality ingredients and expertly blending them to create a dish far greater than the sum of its parts.
I like that. So let's look at these three foundational building blocks that make HNSW truly work. What's the first one?
The first building block is the concept of small world networks. We touched on this briefly with the intuitive idea of human connections. It's based on something most of us are familiar with, the 6 degrees of separation.
Right, the idea that you're connected to anyone through just a few people.
Exactly. This is the notion that you know your friends directly, and they know their friends. And surprisingly, you can reach almost anyone else in the world through a surprisingly short chain of connections, often just 6 or fewer steps. That's the essence of the small world phenomenon.
It's fascinating how that intuitively makes sense in our social lives. You think about how you might be connected to someone famous or a distant relative on the other side of the world through just a handful of mutual acquaintances. That feeling of surprising closeness.
Precisely. And in a formal mathematical sense, small world networks exhibit 2 key characteristics that HNSW brilliantly leverages. First, they have a high clustering coefficient.
High clustering, meaning things group together.
Exactly. It means that nodes, whether they're people in a social network or data points in an HNSW graph, tend to form tight-knit groups or clusters with many connections within those groups. Think about your close circle of friends. It's highly probable that many of your close friends also know each other and are connected. They're tightly clustered.
Yeah, that resonates. My friends' friends are very often my friends too. It's that feeling of being part of a close community. Makes sense.
The second characteristic, which is where the magic truly unfolds, is a low average path length.
Low path length, so it's quick to get between points, even if they're in different clusters.
Exactly. This means that despite this high clustering within groups, you can still reach any node from any other node in the network in just a few steps. How? Because within these clusters, there are also a few long-range or bridge connections that jump across otherwise distant clusters.
The shortcuts.
These long links allow for surprisingly rapid traversal across the entire network.
So HNSW takes this profound idea and applies it directly to data. Instead of people, data points, those high-dimensional embeddings are connected to other highly similar data points.
Imagine a dataset where items that are conceptually very close are tightly clustered, but then there are also a few carefully chosen bridge connections that allow you to jump across different, less similar clusters quickly.
This strategic design forms a network where you can navigate from any point to any other point or find similar points with remarkable speed.
And this concept isn't something that just emerged with HNSW. It was formalized mathematically by the pioneering work of Duncan Watts and Stephen Strogatz in their influential 1998 paper.
Okay, so it has a solid theoretical basis from way back.
Absolutely. Their research provided the theoretical bedrock for understanding how these kinds of networks operate, making them applicable far beyond just social structures. They've been used to model everything from biological neural networks to power grids, and crucially for our discussion, data search algorithms.
Wow, versatile.
Their work showed that you could have both local cohesion and global reach simultaneously.
Okay, so we have the powerful idea of small worlds where everything is surprisingly connected. But simply being connected isn't enough, right? Imagine a city where every street leads to every other street without any road signs.
Exactly. You'd be lost. The real brilliance comes when those connections become navigable, which brings us to the next crucial idea: navigable networks. This is where the network structure actually helps you move in the right direction towards your target.
Like having those road signs.
This is precisely where the navigable small world NSW algorithm comes in. It's the direct, crucial precursor to HNSW. NSW introduced the core concept of greedy routing.
Okay, greedy routing sounds a bit like always taking the closest thing. How does that work in practice when you're searching for data?
It's remarkably straightforward, yet deeply effective.
Yeah.
Imagine you start at an entry point in the network, a data point you just landed on. From that current position, you immediately look at all the directly connected neighbors to where you are.
Okay, check the neighbors.
Among those neighbors, you identify the one that is closest to your ultimate target, the query point. You then immediately move to that closest neighbor.
Just jump to the best one nearby.
You continually repeat this process, always making the locally optimal choice by moving to the neighbor that gets you geometrically closest to your target. You continue this until you can't get any closer. That is, you've reached a point where all your direct neighbors are actually further away from your target than your current position.
So it's like always picking the shortest visible path in your immediate vicinity. You don't necessarily know the absolute shortest path globally, but you're always taking the best immediate step forward based on what you can see right now. Like climbing a hill by always taking the steepest upward step.
Exactly. You're making locally optimal decisions, hoping that this sequence of best local steps leads you to a globally near optimal result. And the remarkable thing about this greedy search is its incredible efficiency. It boasts a polylogarithmic time complexity.
Polylogarithmic. Okay, that sounds fast. How fast?
It's often expressed mathematically as O log n. Now, we don't need to dive deep into the math, but the intuition is key. N is the number of data points. Log n is already much, much smaller than n. The k represents a small, constant factor, often related to the number of layers in the hierarchy, which we'll discuss next. So instead of a simple logarithm, it's a logarithm to a small power.
But still way, way faster than checking everything.
Orders of magnitude faster. This means the growth in search time as the dataset scales is still incredibly slow, far, far less than linear.
So to put that into perspective, what does O log n actually mean for performance in the real world, like compared to checking every single point?
It's the difference between a search taking potentially hours or even days on a vast data set and one that completes in milliseconds. For instance, if n represents a billion data points, a linear search, it would require, well, a billion comparisons.
A billion? Ouch!
But a logarithmic search would take roughly 30 comparisons. Even with a small k, say 2 or 3, a polylogarithmic search is still astronomically faster than a linear one.
30 versus a billion. Okay, I get it. That's huge.
This fundamental shift is what enables real-time recommendations for billions of users, instantaneous image searches across petabytes of data, or even lightning-fast retrieval in large language models. It transforms what's computationally feasible.
Moving us from eventually we'll find it to it's there, now.
Exactly. It's a geometric leap in efficiency.
That's a truly profound leap in efficiency right there. But HNSW adds one more ingenious twist, which is our third and final foundational building block, the hierarchical structure. This is where HNSW truly gets its H and fundamentally differentiates itself from its predecessors like NSW.
Yes, creating multiple layers, much like a skyscraper with different floors, each serving a specific navigational purpose. This brilliant layered approach is actually inspired by an older, clever data structure called skip lists.
Skip lists? I vaguely remember those. They also had layers, right?
They did. The layered approach is absolute key to HNSW's unparalleled performance. Let's really visualize these layers, moving from the top down, just like navigating our data city from a high altitude.
Okay, the skyscraper view.
At the very top floor, layer L, you find very few data points. These are like your express highways or even airline routes between major cities. They have long-distance links, allowing you to make incredibly huge jumps across the data space very quickly.
Getting you into the right general neighborhood with minimal steps.
Exactly. Crucially, our sources indicate that the probability of a node appearing at layer L decreases exponentially, specifically about 1 to L. This means these top layers are deliberately sparse, but incredibly powerful for broad navigation.
Okay, sparse at the top, then the middle.
Then, as you descend, you have the middle floors.
Right.
These layers contain progressively more data points than the top, but still fewer than the bottom. Think of these as your main city roads, not expressways, but not local alleys either.
Right, medium distance connections.
Allowing for more refined navigation than the express highways, but still significantly faster than traversing every single local street. Each layer down progressively includes more nodes and shorter range connections, providing a more detailed view as you get closer to your target.
And finally, the ground floor.
And finally, the most crucial layer, the bustling metropolis, is the ground floor, or layer 0. This is where all the data points reside. Every single item in your dataset, every embedding, every unique piece of information is present here.
Everything's on the ground floor.
Everything. It's connected by short-distance connections. These are your local streets and intricate alleyways. Once you've descended to the ground floor, this is where you perform the fine-grained, precise search to find your exact destination, the most similar data points to your query. This layer offers the highest density of connections and the most granular detail.
And the cleverness extends even to how individual nodes are assigned to these layers, right? It's not arbitrary.
Not at all. Each node's highest layer is chosen probabilistically when it's added, using an exponentially decaying distribution. This is very similar to how skip lists probabilistically build their multiple levels of links.
So most points just stay on the ground floor.
The vast majority will only be on layer 0. Fewer points will randomly get assigned to also exist on layer 1, even fewer to layer 2, and so on. This probabilistic assignment ensures that those sparse top layers with long-range connections are indeed sparse, making those highway jumps incredibly efficient while maintaining robust connectivity across the entire graph.
It's a brilliant way to build a balanced, multi-scale map.
Exactly. It's the architecture that enables the speed.
So we've broken down what HNSW is, the scale of problem it solves, and the fundamental building blocks it ingeniously combines. Now let's bring it all together and truly visualize how HNSW actually finds a similar data point in practice. Imagine we have our multi-layered data city map, our HNSW index, already meticulously built and ready for navigation.
Okay, let's walk through an example. The diagrams we often see for HNSW visualize this perfectly, illustrating the journey. You clearly see those distinct layers. Layer 2 at the top maybe representing our sparse express highways.
And layer 1 in the middle, our main city roads.
And layer 0 at the very bottom, the dense network of local streets containing all our data. The green circles within these layers represent our data points, our embeddings, those numerical fingerprints.
And the red rectangle, that's our query, the thing we're looking for similarity to.
Precisely. The item we're looking for, the thing from which we want to find similar items, the ultimate goal here is to find the approximate nearest neighbor to that query.
And the key word there, which bears repeating, is approximate.
Absolutely. If we were to do a brute force search in this small example where we might have, say, 12 data points in total, we'd have to calculate the geometric distance between our red query and each and every one of those 12 green points.
That's 12 distance computations. Okay, manageable for 12, but not for billions.
Exactly. HNSW aims to do this with far, far fewer computations, saving immense amounts of time and resources, especially at scale.
And looking at the diagrams, you see the same point can appear on multiple layers.
Yes, a crucial detail is how identical data points are conceptually projected or exist on higher layers. You often see dotted lines connecting the same green circle across different layers. But importantly, the connections, those blue lines representing links between data points, in higher layers do not necessarily mirror or directly correspond to those in lower ones.
Ah, okay. They serve different purposes.
Exactly. The links in the top layers are designed for broad, sweeping jumps across the data space, while the links in the bottom layer are for fine-grained local exploration. That's a core part of the optimization. Different layers serve different navigation purposes to achieve overall efficiency.
Okay, with our map ready and our query in hand, let's embark on this guided tour. How does it start?
Step 1. We begin our search by entering the HNSW index at some designated entry point in the topmost layer available. In many diagrams, this might be layer 2. This initial point acts as our starting guide, our entry ramp onto the highest highway. Let's say, for simplicity, we begin at the point labeled 1 in layer 2.
Step 2. Now we perform that greedy search within this current layer. This is the core navigation process we discussed earlier, always choosing the path that gets us closest to our destination, the red query.
Right. First, we compute the distance between our current entry point, point 1, and our red query point. Then we look at all the directly connected neighbors of point 1 in this current layer, layer 2, and compute their distances to the query as well.
Okay, compare the current spot and its neighbors to the query.
Out of point 1 and its available neighbors, we identify the point with the smallest distance to the query. In our example, maybe point 1 has only one neighbor, point 2, in layer 2. We compare the distance of point 1 to the query and point 2 to the query.
And if point 2 is closer?
If point 2 is closer, which it often will be, it immediately becomes our new entry point within this layer. We then repeat this process. From this new entry point, point 2, we check its neighbors in layer 2.
But what if it has no other neighbors in this layer, like in the diagram?
Good point. If we reach a point, like point 2 in this case, where the closest point to the query is our current entry point, or if that closest point has no further unexplored neighbors in this layer that would get us closer, then we know we found the best possible jumping off spot in this specific layer.
So in our layer 2 example, let's assume point 2 was closer than point 1. It becomes our new entry point. Since point 2 has no other unexplored neighbors in layer 2 in this diagram, we've effectively found the most optimal position within this highest layer. We've made our initial broad long-range jump.
And we're now ready to descend to the next level of detail.
Mm-hmm.
Step 3. We move down one layer and repeat the greedy search, but with a refined starting point.
Okay, dropping down to layer 1.
So we transition from layer 2 down to layer 1, using point 2, our best candidate from the layer above, as our entry point in this new, more detailed layer. We already know the distance between point 2 and the query from our previous calculation, so we reuse that. Smart saves computation.
Nice.
Now, we compute the distances to point 2's neighbors in layer 1. In the diagram, these might be points 3 and 4.
We compare point 2, point 3, and point 4 to the query. Let's say point 4 is now the closest among them. Point 4 wasn't our initial entry to this layer.
So it becomes our new entry point within layer 1. We then check point 4's neighbors in layer 1. Let's say it has a new neighbor, point 5. We compute the distance to point 5.
So compare point 4 and point 5 to the query now.
Right. And let's say after this new comparison, point 4 still remains the closest to our query within layer 1. This means we've effectively found the best spot in layer 1, getting us even closer to our target.
And with no further closer neighbors or unexplored paths in layer 1, we're now ready for our final, most detailed descent.
Exactly. Step 4. Now for the final, most crucial search, we move into the bottom layer, layer 0. This is the layer where all the data points reside and where we'll perform our fine-grained local search.
Starting from point 4, our best from layer 1.
Correct. We start our exploration from point 4. In layer 0, point 4 will likely have many more neighbors, maybe points like 2, 6, and 7 in the diagram example. We compute the distances to these neighbors from our query.
Okay, check 4, 6, and 7. What if 7 is closest?
Out of those, let's say point 7 is now the closest to our query. Point 7 immediately becomes our new entry point in layer 0. We then recursively look at point 7's neighbors. Maybe only point 8 is an unexplored neighbor.
Check point 8's distance.
We check point 8's distance to the query. After this final check, maybe point 7 remains the closest point to our query. At this stage, there are no more unexplored neighbors connected to 7 that would get us any closer. The greedy search at layer 0 has reached its local minimum.
And the search terminates.
The search terminates.
Yeah.
Step 5, we return the approximate nearest neighbor. In this specific walkthrough, the algorithm returns point 7 as the approximate nearest neighbor to our query.
And here's where we truly grasp the efficiency. Remember how a brute force search would have required 12 distance computations for this tiny example?
Right.
In this HNSW walkthrough, how many did we do? Say, distance to 1, 2, and L2, then reuse 2, add 3, 4, and L1. Reuse 4, add 5 in L1. Reuse 4, add 6, 7 in L0. Reuse 7, add 8 in L0. That's only 8 distance computations.
Exactly. Only 8 computations were needed to find a very close match. And while saving 4 computations might not seem like a massive difference in a small illustrative example with only 12 points.
It's absolutely crucial to emphasize that in real-world scenarios with optimized graphs and datasets containing millions, billions, or even trillions of data points, the efficiency gains are truly monumental.
Astronomical. This is what allows HNSW to power instantaneous search results for massive platforms. It's the difference between a system grinding to a halt and one that feels magical in its responsiveness.
But it's important to remember, again, that HNSW does not guarantee finding the absolute exact nearest neighbor because of its greedy nature and the layers.
It's an approximate solution. However, it typically finds a very, very close match, often within a tiny fraction of the distance to the true nearest neighbor. For most applications, this trade-off of a slight approximation for massive speed and scalability is not just acceptable, but incredibly worthwhile. It allows systems to function at scales that would otherwise be completely impossible.
Got it. So approximate, but usually extremely good and blazingly fast.
That's the core trade-off and benefit.
Now that we've seen how HNSW performs a search, cleverly navigating from coarse, high-level layers to fine-grained local layers using that efficient, greedy routing, it's equally important, perhaps even more so, to understand how this incredibly powerful and intricate structure is built in the first place.
Right, how do you build that smart city map? Imagine you're starting from scratch, where every building, every data point needs to be strategically connected to others in a way that helps you find the fastest route later on. That's what constructing the HNSW index is all about.
So, step 1. We start with an empty graph. Just nothing there.
Exactly. At the very beginning, there's no structure, no connections, just an empty conceptual space waiting to be populated. When you insert the very first data point into this empty graph, that point becomes special. It's automatically designated as the entry point for all subsequent insertions of new data. And critically, it also serves as the initial entry point for all future similarity searches. It's like the initial foundational landmark in our newly imagined data city.
Okay, the first point is the starting gate. Then what?
Then comes step 2. Assign a height or layer to each new data point. As new data points arrive for insertion, HNSW needs to decide which layers of the hierarchy that new point will reside in. You can visualize each data point as a building in our city.
Some tall, some short.
Exactly. Some buildings are conceptually tall, meaning they appear in higher layers of our HNSW graph, acting as those important highway nodes. Others are short, and they only appear on the ground floor, layer 0. The height, or the highest layer a point appears in, is chosen probabilistically and randomly when the point is inserted.
Randomly. But there's a pattern, right? You said tall buildings are rarer.
Correct. It follows an exponentially decreasing probability distribution. So, to break down that probabilistic assignment, it means that the vast majority of points will only appear on the ground floor, layer 0, where all data points reside.
Okay.
Fewer points will be chosen based on this probability to also exist on layer 1. Even fewer will make it to layer 2 and so on for higher layers. This highly skewed probabilistic assignment is absolutely critical because it ensures that those sparse top layers with long-range connections are indeed sparse.
Which makes those highway jumps incredibly efficient. If the top layers were dense, it would defeat the purpose.
Precisely. This layered structure, built this specific way, is what allows the algorithm to zoom in effectively, transitioning smoothly from a broad overview to fine details. It's the architectural blueprint for the algorithm's multi-scale efficiency.
Okay, so we've assigned a height. What's next?
Once a point's height, its layer assignment is determined, we move to step 3. Insert the point into the graph and connect it. This is where the core construction logic plays out for each new data point as it's added.
This sounds like the tricky part.
It involves a few sub-steps. First, A. Start at the top layer for search. When a new point needs to be inserted, we begin the insertion process at the highest layer where the current global entry point exists. Remember, this entry point is typically the most recently inserted node or a pre-designated one.
Okay.
From there, we perform a greedy search. But this time, instead of searching for a query's nearest neighbor, we're searching for the best place to connect our new point within that specific layer.
So finding its neighborhood.
Exactly. We look at the neighbors of our current position in that layer and move to the one that is geometrical closest to the new point being inserted. We repeat this until we can't get any closer to our new point in that specific layer. This initial search helps us find the neighborhood where the new point semantically belongs.
Got it. Find the rough area first, then.
Then B, move down one layer and refine. Once we've found the best spot for our new point in the current layer, essentially, identifying where it best fits in terms of similarity, we descend to the next lower layer. We resume the greedy search from the point we identified in the previous layer as the closest or best fit for our new node.
So search, descend, search again.
This process of searching and descending continues layer by layer, progressively refining the new node's ideal placement and connections, until we reach layer 0, the ground floor, where all points reside. This multi-level search during insertion ensures the new node is well integrated across the hierarchy.
And then the connections happen.
Yes, and here's a crucial part of building the small world structure. C, connect to neighbors at each layer. At each layer, the new point is inserted into. From the top layer is assigned down to layer 0. It connects to its m closest neighbors that are already in the graph at that specific layer.
That sounds like a setting you can choose.
It is. M is a key parameter we'll discuss in detail next, but it defines the maximum number of connections each point can have at each layer. These connections are absolutely critical. They are bidirectional.
Bidirectional, meaning if A connects to B, B must connect back to A?
Exactly. This bidirectional linking is fundamental to how the small world network is created and robustly maintained within each layer, allowing for incredibly fast two-way traversal. It ensures that the graph remains balanced and navigable in both directions. Without bidirectionality, paths might become one-way streets, breaking the efficiency of the greedy search.
Makes sense. Like having two-way roads instead of just one-way streets everywhere.
Yeah.
So, step 4. This process just repeats for all points.
That's right. Every single new data point you add to your dataset goes through this same procedure. Assign a probabilistic height, search from the top layer down to find its best placement, and finally, connect it to its m closest neighbors at each level it resides in, ensuring those links are bidirectional.
Over time, this meticulous point-by-point process builds the incredibly efficient multi-layered graph that is the HNSW index.
It's like building a city from the ground up, but simultaneously laying out highways, main roads, and local streets, all interconnected, ensuring optimal navigation from the very first brick.
Okay, HNSW is, as we've established, an incredibly powerful algorithm, but getting the absolute best performance from it isn't a set it and forget it situation you mentioned.
No, definitely not. It's more akin to adjusting the finely tuned settings on a high-performance race car engine to extract every last bit of power, speed, and efficiency for a specific track. These critical adjustments are controlled by what we call key parameters.
The knobs and levers.
Exactly. Mastering these allows you to optimally balance accuracy, speed, and memory usage for your specific application.
Let's dive into these knobs and levers for HNSW performance, starting with that one you just mentioned. 1 max connections per node. What does this vital parameter actually control, and what are its real-world implications?
M directly controls how many neighbors each data point connects to during the index construction phase, at each layer it exists on. It's like setting the maximum number of direct roads leading out of each house or business in our data city analogy.
Okay, how many connections per point per layer?
When you insert a new point, the algorithm finds its M closest neighbors in each layer it occupies and establishes those bidirectional connections to them. The trade-offs here are quite clear and fundamental.
Let me guess. Higher M means better accuracy, but more memory.
You got it. A higher M generally leads to better search accuracy, often referred to as recall. Because each point has more connections, the search algorithm has more paths, more alternative routes to explore, making it more likely to find the true nearest neighbor.
But
But this superior accuracy comes at a cost. It uses significantly more memory for storing all those extra connections and can slow down the index build time as more connections need to be established and maintained.
so more connections, potentially better accuracy, but at the cost of memory and build time. That makes sense.
Precisely. Conversely, a lower M value results in a faster index build and uses less memory, which can be crucial for memory-constrained environments. However, you might sacrifice some search accuracy because there are fewer paths to explore. The graph might become too sparse.
Leading the greedy search to get stuck in local minima more frequently, maybe further from the tree best match?
Exactly. So M is a crucial dial for balancing resource consumption against search quality.
Got it. That's a classic engineering trade-off. Next up, we have 2, F construction search breadth during build. This sounds quite technical. What's EF stand for?
EVE usually stands for effective factor or exploration factor. It relates to the size of the dynamic candidate list used during search. This parameter, F construction, specifically controls how many candidate nodes the algorithm considers when it's finding the M closest neighbors doing the insertion process itself.
Ah, so this affects how well the map is built initially.
Precisely. Remember, when a new point is added, HNSW performs that temporary internal greedy search to figure out who its M neighbors should be at each layer. A higher F construction means that HNSW explores a wider range of possibilities, considering more potential candidates during this internal neighbor-finding search.
Leading to a better map.
It results in a much better quality graph, meaning more optimal, truly relevant connections are made across the layers, which ultimately leads to significantly better search accuracy when you query the graph later. It's about investing more upfront effort to build a more robust and accurate map.
Makes sense. Build it right the first time. What's the trade-off?
The trade-off, however, is a slower build time, as more distance computations and comparisons are required during each point's insertion. A lower F construction speeds up the index build process considerably, but might lead to a lower quality graph structure with suboptimal connections.
Which could hurt your search results later on.
Exactly. This, in turn, can mean lower search quality and recall later on because the paths aren't as efficiently laid out. Think of it as how meticulously you draw your city map. Higher F construction means more attention to detail, leading to better navigation for everyone later.
Okay, so F construction is about how much computational effort you put into building a really good, highly optimized map from the start. Then there's 3, F search breadth during querying. This sounds similar, but you said it's used at a different stage.
Absolutely. This is a critical distinction. F-search is used only when you're searching the completed HNSW graph, not during its construction. It controls how many candidate nodes are explored during a query, how wide the search beam is as you navigate through the graph at query time.
So higher F search means look harder during the actual search.
Exactly. A higher F-search gives you better search accuracy and higher recall, because the algorithm explores more possibilities, keeping a larger list of potential best candidates active during the search. Therefore, it's more likely to find the true nearest neighbors. It's like allowing your navigation system to consider more alternative routes and reroute more aggressively to find the absolute best path.
And the trade-off there, slower searches.
This more thorough exploration comes at the cost of a slower search time. More computations are performed per query. Conversely, a lower F-search will give you a faster search as fewer nodes are explored, but you might miss the absolute best matches, leading to lower recall.
So this is the main knob for speed versus accuracy when you're actually using the index.
Exactly. This parameter is often described as the main knob to tune speed versus accuracy at query time, because you can adjust it on the fly after the index is built to meet your specific application's needs.
Oh, that's useful. You can change it without rebuilding.
Yes. For example, a real-time recommendation engine might prioritize a slightly lower F-search for lightning-fast results, while a scientific research application might crank F-search up to maximize accuracy, even if it has a few milliseconds to the search.
That's a really important distinction, that if search allows for runtime tuning based on immediate needs. Finally, we have 4 level multiplier. What's this all about?
The L parameter, sometimes called level mult in implementations, directly affects the probabilistic assignment of a data point to higher layers. Remember how we said fewer points appear in the top layers, following an exponentially decreasing probability? LMIL influences the steepness of that exponential curve.
So it controls how many layers you typically get.
Essentially, yes. It controls the shape of the hierarchy, determining whether you have more or fewer tall buildings in your data city, and thus influencing the average depth of the graph. A smaller L value means points are less likely to be in higher layers, resulting in a shallower graph with potentially fewer long-range connections. A larger L would lead to a deeper graph with more points potentially reaching higher layers.
So it's about the overall architectural design of the hierarchy. How do you even begin to tune all these knobs? It sounds like quite an art form.
It is indeed a balance of science and art guided by your specific requirements. The general advice is to start with sensible default values provided by the library you're using. Often, something like M16, F construction 200, and an ML calculated based on M, like 1 log M, are common starting points, as they often provide a good balance.
Okay, start with defaults, then what?
If you find you need higher recall, meaning you want to be more certain you're getting the absolute true nearest neighbors, even at the expense of memory, you can try increasing M, maybe up to 32 or even 64. This increases the connectivity.
And for F-search, how do you tune that?
You adjust F-search based on your specific speed and accuracy requirements for your queries. You typically benchmark it. Start low, measure speed and accuracy, recall. Increase it, measure again. Find the point where you get acceptable accuracy for the speed you need.
So if you need super fast results, maybe accept slightly lower accuracy?
Exactly. If you're building a real-time recommendation system where latency is paramount for user experience, you might start by tuning F-search downwards, accepting slightly lower recall for sub-millisecond responses. But if you're in bioinformatics searching for highly similar protein structures, where accuracy is king and query time is less critical, you'd prioritize a much higher F-search value, willing to wait a fraction longer for a more precise match. The key is to understand your use case.
And the absolute best way to find the optimal settings for your specific data and your specific needs, there's no magic formula.
No magic formula. The best way is through rigorous benchmarking tools and empirical testing. You run controlled experiments on your actual data, measure performance, speed, recall, memory across different parameter combinations, and iterate. It's a process of continuous empirical optimization to hit that sweet spot for your particular use case.
So measure, tweak, measure again. Got it.
Exactly. The optimal parameters are highly dependent on your dataset's characteristics and your application's demands.
We've broken down the what and the how of HNSW. Now let's zoom out and consider the why and the when. Why does HNSW work so incredibly well, achieving these seemingly impossible feats of speed and accuracy? And when is it the absolute best tool for the job versus when should you consider alternatives?
Right. This is where we bring it all together. The breakthrough of HNSW truly lies in the power of its combination, the masterful synthesis of those 3 building blocks we discussed: small worlds, navigable connections, and the hierarchy.
It's the synergy.
Precisely. The ingenious part is how it uses those sparse top layers, those express highways, to allow for incredibly big jumps across the vast data space. They quickly get you into the right general area, bypassing millions or even billions of irrelevant data points in just a few hops.
Then, as you strategically descend through the middle layers, you gradually zoom in.
Until you reach the bottom layer, layer 0. That's where you get the fine-grained detail, like navigating local streets to find your precise destination, your specific similar data points.
So it's that seamless multi-resolution transition from broad strokes to detailed precision that makes it so remarkably effective and efficient.
Absolutely. The search always starts from a known entry point. It relentlessly uses greedy routing to navigate towards the target within each layer, reaching a local minimum at each level where it can't get any closer in that layer. Then it strategically descends, carrying forward the best candidate found above.
This iterative descent, continually refining the search path.
Means it ends up performing a highly refined search at layer 0, where all the data lives. And as we discussed, the algorithm can be configured to return not just one, but multiple approximate nearest neighbors, KNN search, which is vital for many applications.
And the result.
The result is that this clever, multi-layered combination makes HNSW both incredibly fast and remarkably accurate, even for truly gigantic datasets. We already highlighted the efficiency, but it bears reiterating the logarithmic search complexity, O log n.
Compared to the linear ON of checking everything.
It's vastly superior. For a dataset of 1 billion items, ON means 1 billion operations. Olovaga might be just around 30 operations. Even with that small K factor, the difference is astronomical. It makes real-time search on massive scales a reality.
And this wasn't just a lucky guess. There's deep science behind it. You mentioned the 2016 paper by Malkoff and Ashunin.
Yes, efficient and robust approximate nearest neighbor search using hierarchical navigable small world graphs. Public first on Archive, then formally in IE transactions on pattern analysis and machine intelligence. Very well-respected venues.
Cementing its academic credibility.
And the impact shows. Cited over 2,000 times, become a de facto standard in many industries. The core innovation, the genius, was that synthesis, combining skip lists.
Invented by William Pugh in '89, right? For fast searching with levels of links.
Exactly. Combining that multi-level concept with navigable small world networks, building on John Kleinberg's brilliant work on creating smart connections for efficient navigation. HNSW essentially applied the multi-level skip list idea to a navigable graph structure.
So it's a brilliant fusion of established, powerful ideas brought together in a novel way.
Precisely. While the math can get complex, the core insights are elegant. The logarithmic search complexity is key to speed. The M connection strategy balances accuracy and resources.
And it's theoretically sound.
Very much so. The algorithm is mathematically guaranteed to reach a local minimum at each layer during the greedy search. And the hierarchical structure significantly increases the probability that this local minimum is very close to the global optimum, meaning you're highly likely to find a fantastic match.
Supported by concepts like scale separation.
Right, where upper layers provide those long-distance jumps, separating the search into different scales. This leads to the polylogarithmic complexity, O log n, and high probability guarantees for near-optimal results. It's robust, both in practice and theory.
So that's a comprehensive look at why it works so well. But what about the trade-offs and limitations? Nothing is perfect, right?
Correct, no silver bullets. The first and perhaps most important limitation to reiterate is that HNSW delivers approximate results by design.
It might miss the absolute exact nearest neighbor occasionally.
It might. However, typical recall rates are exceptionally high, often 90% to 99%. This means it finds the true nearest neighbor 99% of the time, or at least a very, very close substitute. For most applications, recommendations, image search, chatbots, this trade-off is absolutely worthwhile for the speed gain.
Okay, approximation is the main one. What else?
Parameter tuning, as we just discussed. It's not set it and forget it. It requires careful adjustment of M, if construction, F search, ML, to get optimal performance for your specific data and needs.
Requires some effort and benchmarking.
Definitely. Another significant practical consideration is dynamic updates. HNSW is best suited for mostly static datasets.
Meaning data that doesn't change constantly.
Exactly. Datasets where additions and deletions are infrequent or happen in batches. While HNSW supports insertions, frequent insertions and especially deletions can degrade performance over time. The carefully built graph becomes less optimal.
So the map gets outdated.
Kind of. It might require periodic rebuilding of the entire index for peak performance, which can be time-consuming and resource-intensive for very large datasets. Dynamic updates also add complexity with synchronization if multiple processes modify the graph.
That's a crucial point for real-time systems. Okay, what else?
Finally, there are distance metric limitations. While HNSW is versatile, it performs best, and its theoretical guarantees are strongest. With common metrics like Euclidean distance, L2, and cosine similarity.
Why those specifically?
They are mathematically well-behaved in high-dimensional spaces, which aligns with the geometric assumptions HNSW relies on for greedy routing. If your application needs other more complex or unusual distance metrics, HNSW might require modifications or just perform suboptimally.
So stick to Euclidean or cosine if possible for best results.
Generally, yes. It's optimized for those.
Okay, so given these powerful benefits and these practical limitations, when is HNSW truly the ideal choice, the go-to algorithm?
It's perfect when you urgently need fast similarity search in very large data sets. Millions, billions of items, product images, user profiles, documents where you need quick recommendations, search results, content matching. HNSW is often a top performer.
And when accuracy needs to be good, but maybe not absolutely perfect 100% of the time?
Exactly. If you require good accuracy, high recall, with reasonable speed, you get excellent results, orders of magnitude faster than brute force. It also shines if your data is inherently high-dimensional.
Like those complex embeddings we talked about?
Yes, image embeddings, text embeddings from LLMs, intricate user profiles. And finally, if you need scalable solutions that grow efficiently with your data, HNSW's logarithmic complexity means it handles growth much better than linear methods.
Okay, so when should you maybe look elsewhere?
Well, if you absolutely unequivocally need guaranteed exact results. If missing the true nearest neighbor is completely unacceptable, certain scientific calculations, maybe some financial modeling, then HNSW's approximate nature is a deal breaker. You'd need an exact algorithm, which will be slower.
Makes sense. What else?
Also, if your data set is very small, say just a few thousand items, the overhead of building and managing an HNSW index might not be worth it. Simpler, traditional methods like brute force might be easier and fast enough.
Good point. Use the right tool for the job size.
And if memory usage is a critical constraint, HNSW can be memory intensive, especially with higher M values storing all those connections. If you're on a very tight memory budget, you might need more memory-efficient alternatives, perhaps sacrificing some speed or accuracy.
And the dynamic updates issue.
Right. If you need to frequently add or remove data in a truly dynamic, real-time fashion, HNSW's optimization for mostly static datasets means it might require careful management, like batch updates or periodic rebuilding, which adds overhead. Other structures might handle churn better, perhaps at the cost of query speed.
What a journey. We've really taken a thorough exploration into hierarchical, navigable, small world. It's clear that HNSW represents a monumental breakthrough in how we search for similar information across truly vast, high-dimensional data sets.
It really is. It's a testament to clever algorithmic design, meticulously organizing data in multiple layers with smart bidirectional connections that allow for both those express highway jumps and incredibly precise local street searches.
It truly is fundamental to the speed and intelligence of so many digital services you use every single day, often without even realizing the sophisticated machinery quietly at work. Recommendations, image search, semantic search.
Understanding HNSW gives you a fascinating peek behind the curtain of modern technology. It's a cornerstone of the AI and data revolution we're living through.
And as data continues to grow, not just in volume, but complexity, think beyond text and images, maybe to scientific models, autonomous system understanding, what new dimensions will we need to navigate?
That's the big question. How might algorithms like HNSW need to evolve to find similarity in an increasingly intricate and ever-expanding digital world? Maybe searching through representations of emotions or complex system states.
It's a question that pushes the very boundaries of what's next in intelligent search and discovery, a truly fascinating thought to leave with.
Indeed, the quest for smarter navigation through data is never-ending.
Thank you for joining us on this deep exploration.